Hi, this is Shuley Physics APC Mechanics Exam Review 6 on torque, rotational stacks, dynamics and energy, and angular momentum, also some conservation of angular momentum. All right, we're starting off here with the analogs of Newton's second law, kinetic energy, and momentum. These are our main focuses here in this session. Instead of a net force equals ma, we're going to have a net torque on a rotating body equals I alpha. So everything you learned about Newton's second law with force diagrams and everything applies here also. Just remember when you're doing these force diagrams, you're going to apply the force at different parts of the object. Don't just be generic like on the middle of the object on the force diagram. So if there's a force on the edge of an object, you'll specify it's on the edge. Normal forces will come from the surface out, perpendicular. Gravity is always from the center of the center of mass of the object down towards the center of the earth. So it's important to remember that. The rotation, instead of 1/2 mv squared, we got 1/2 I omega squared for rotational kinetic energy. And angular momentum, we got two forms of that. Think P equals mv. Well, then for a rotating object like a fan or something like that, you take I times omega instead of mv. It's a rotational mass, or rotational inertia, times the angular velocity. Now for a point mass that is rotating about a body, think like a planet around the sun, or an object on a string that's rotating, or it could be an object that's not even attached to a rotational axis, but maybe in the very, very near future is going to be attached somehow. Let's take say a skateboarder jumping onto a merry-go-round. I know we probably did that if you had my class. So that would be, just think MV. It's like MVR, okay? But so we do have momentum in there times the rotational, the radius about the rotational axis. But you take mr cross v. And so if you have that skateboarder of mass m, take r cross v, wherever the skateboarder is going, it is at the moment, that's the r, and of course the v is the velocity of the person who's just about to jump onto the merry-go-round. But a planet around the sun is also the same kind of thing. It has a mass, it has a velocity, and also changes its r value. So that comes in the gravitation oscillations section next, in the next review session. All right, so a couple of tools just to remind you about, to keep them in your back pocket. S, the arc length equals r theta. That's the relationship between the angular position and the arc length, or I guess angular displacement. We got v equals r omega and a equals r alpha. So remember all those. The v would be the edge speed, a up here would be the edge acceleration, omega is the spinning speed, and of course something to also remind you of here that's going to be especially important when we're looking at translational kinetic energy is that, let me make that look good. Okay, is that with v equals r omega, this is for the edge velocity, but that v is also equal to the center of mass translational speed as well. And I covered that a little bit more detail in the last session, session 5. So take a look at that if you need more on that. All right, torque. What is torque? Torque equals a force at a position away from the axis of rotation. Now, if that force is applied inward toward the axis of rotation, you're going to get zero torque. So it's only the perpendicular component that matters. So if you take r cross f, that's going to give you fr sine theta. Is generically what we usually use for torque. Just always think about that sine theta if there's an angle involved. Now, if all the angles between the r and the f is 90 degrees, then just recall sine of 90 is 1, and torque equals force times torque arm. That'd be F times torque arm is the R. So in a case of like a seesaw or a balance, got a fulcrum in the middle, and there's a force, unknown force placed out here at R3, and we want to know how to balance the torques due to this 10 Newton force at R1 and the 30 Newton force at R2. We're going to take sum of the net sum of the torques, the net torque equals I alpha. And in this case, if we're trying to balance it, what is alpha? Alpha is going to be 0. So all we have is F times R3 minus 10 times R1 minus 30 times R2 equals I times 0 angular acceleration. And that would give us a balancing force and equation to work with. Or let's say, I think I give a painter or a window washer out on a building. So you might have a torque 1 going up this way at a weight of a person standing on it. You've got the weight of the beam and the weight of the water or the paint bucket over here. And then there's also tension 2. So which one would have a greater tension, tension 1 or 2? It's probably going to be 1 over here. But you can actually figure out the exact amount. Now, when you're doing this, when you're solving a problem like this, oh, I'm going to get to that down there. Okay. So lastly, generically, how else, what's another situation you might use torque? If there's a rotating body and a force being applied at a radius, it's going to cause an angular acceleration. And you might also, with the rotational statics kind of scenario, you might also have something like this, a couple of beams, maybe a tension holding that beam, and maybe a mass somewhere out on it. Keeping in mind that angular acceleration is 0. So these are some generic situations that might pop and be like, oh, I got to apply torque and Newton's second law for torque over here. All right, so here's some specifics. This is rotational statics and dynamics right here. That's what I was referring to in the title. So if we do have that object of 150 kilograms, the center mass of the beam, which is 100 kilograms, is located at the center. If a problem ever gives you the mass of an object like the beam, but doesn't really say anything else, then you assume that it's a uniformly distributed mass, and that means this 100 kilograms of mass can count at the center of mass. So on your force diagram, that's where you would apply that force. And let's say there's a bucket of something that's 50 kilograms over here, so there's a weight of that, there's a weight of the beam, there's a weight of the person, it's 150 kilograms of mass, interpreting into a weight there. If we want to know what the tensions in the cables supporting the beam is, that would be tension 1 and tension 2. So what do you do first after your force diagram? Well, just make sure you consider what are the R's and what are the angle thetas. So here, each of our R's are probably going to be along this beam, so all of the forces are at an angle of 90 degrees. So we can cut out the angle, don't worry about that. Sine of 90 is 1. The next thing, you want to pick a reference point. I like picking a reference point that's underneath one of the unknowns. Now, if you only have one unknown, don't pick a reference point under that unknown. And what I mean of that, pick a reference here. The R value to that unknown is going to be 0 from this reference point. Now, this reference naturally for something like a merry-go-round with a natural spinning axis, that should be your reference point if there's a natural spinning axis. But just think about this. If tension 2 broke, then everything would kind of swing down this way. All right, it would rotate about this point. If tension 1, if this cable broke, then it would kind of swing down, the system would swing down this way. So you can really pick any point here. If both of them broke, the whole system might start spinning about the center of mass. So you could pick that as a reference also. Just pick a natural reference to work with. I'm going to take that off. I might need some references later. So if this is my reference point, then I'm going to start building my equation, my Newton's second law equation for rotation. Net torque equals I alpha. So from this point, tension 1 is applied at 0 torque arm. The weight here, 150 times 9.8, don't forget to multiply by 9.8. Or just be careful here, sometimes the weights of the objects are given. If you're given weight, don't multiply by 9.8 again. It's mass times 9.8 is weight. It gives us a torque arm of 1 here. So 1 from the reference. So we're going to take the weight times the torque arm of 1. Here's the center of mass. Don't forget that. 100 kilograms for the beam times 9.8 is its weight times 2 meters. Now it doesn't really specify the distance here, but if the whole beam is of length 4, then the center mass is at 2. And then we'd have this chunk of this bucket or something over here holding paint. So it's 50 kilograms times 9.8, and it's 3 meters away. And finally, we'd have tension 2 over here going up, and that is an unknown as well, and it's 4 meters away from a reference point. Now let's look carefully at the positives and the negatives I gave this. You got to think about rotation. This board wants to the weight over here wants to make the board rotate counterclockwise. I'm sorry, positively clockwise. All right. Center mass also wants to make the board rotate clockwise about this reference point. The bucket of paint wants to make the board rotate clockwise. Oh, and I missed this one. The tension one over here doesn't make it rotate at all. It has 0 torque arm, so you actually don't have to worry about that. The torque is 0 from that tension 1. But finally, tension 2 over here, what's it trying to do? It's trying to rotate the system counterclockwise, up that way. So in terms of forming your rotational, your torque equation, Newton's second law for torque, there are 2 directions. There's positive and negative, which can be like clockwise or counterclockwise, or you might say counterclockwise is positive and clockwise is negative. So just keep it consistent throughout, and go with that. So that sets up your equation, and but you have only one unknown, okay? And you can solve for that T2. Now, if you did use the center mass as your reference, you would have different torque arms, but you would also have an equation with 2 unknowns, and you wouldn't be able to solve it. So solving this equation over here that I've formed will give us an answer for T2, but it doesn't give us an answer for T1. You see, it's blocked out over here. It's a 0. So what you're going to have to do is form a second equation. Remember, when you get stuck, don't stop. What about T1? So there's 2 things you could do here. You can either, in this scenario, you could rewrite this whole equation with a reference point under T2, and that will give you an equation involving only tension 1. That's one way to do it. But the other thing is, this is a static scenario, not only in the translational kind of or rotational kind of dimension, but also in the translational view as well. So you can also apply Newton's second law for translation. You see these 2 tensions are supporting all of the weight that's on this board. So it's also in translational equilibrium. The rotational acceleration is 0, and also the translational acceleration is 0. So tension 1 plus tension 2 minus all those weights equals 0 as well. Once you know tension 2 from this, we can plug it in over here and solve for tension 1. So there's many ways you can go about it. I recommend getting a torque equation and a force equation using Newton's second law. And that generally solves any scenario you need to look at in rotation. So here's another one. The beam with the mass on the end and the tension. Now I made this one really funky on purpose. I'm going to fly through it right now, but I really recommend you looking at the notes to get all these little details out, because there's some funky angle stuff going on here. All right, so here the torque equation is going to involve a mass here, looks like a mass of a beam, and a tension that's going up here. So I'm going to use this as a reference point, so I don't have to worry about this board putting any force. But if you ever do have to draw a force diagram for like this middle beam here, you would have to include the force from this peg out here. So just keep that in mind. It's going to be doing something to the system here. All right, so if we look at this beam, there's a oh, you know what? I made it a little easy here. I said there's a low mass board. We can probably count that out. As long as that there's an insignificant mass, it's not going to have a big effect on the torque equation. So I think that's what I did here, just to simplify it a little bit. But if you did have that mass of the board that's significant, you would have to add in another torque down here. Okay, but our main torques are from the tension in the wire and the weight on the end. It's going to have a much more significant mass. See, this 10 kilograms is going to be much more significant than the 5, especially because it's way out here on the end. Greater torque arm is going to give you much more torque. So we're going to apply torque equals R times R cross F, and that is FR sine theta in each case. So we have this 98 newtons from the 10 kilogram force way out here on the end, and the R is in this direction, out here. That's greater than 90 degrees. So if you look at the inclination of the beam, it's 30 degrees. We're going to add 90 plus 30 is 120 degrees. So this mass out here on the end is going to have a torque of mg, or 98, times 5 meters. That's the length of the entire board. So FR sine of 120. And subtract from that the torque from this tension. The tension is 2 meters away from the reference point. So we're going to have tension times 2 sine 130. If you do the math with 50 degrees and an inclination 30 plus another 90. So that, sorry, that would be, that would work it out there. If this angle is 50 and this angle is 30, then the angle between R that goes out this way and T is 130 degrees. So that's T2 sine 30. Now we're going to subtract that torque from the original one because the mass on the end is trying to rotate the system counterclockwise. It's trying to rotate the system clockwise, and the tension is trying to rotate the system counterclockwise. So they're going to be in opposite directions. This one's a positive, and this one is a negative over here. Now, if the system is at rotational equilibrium, which it is, the angular acceleration is 0. We're just going to have a 424 minus 1.53t equals 0, and we solve for that tension in the cable. And what if the cable snaps? What would be the angular acceleration then? We're going to have two things happening here. We're going to have the bar rotating, and we're going to have the mass translating. Whoa, what's up with that? Okay, so with the bar rotating, we're going to have only the torque from the bar left. We're not going to have the torque from that tension because that tension snapped. So we're going to have 5t sine 120 equals I alpha. Okay, and the I would be the I for the bar, 1/3 ml squared. You can look that up, or the problem is probably going to give it to you. And we're also going to have the mass translating over here. So the mass translating, we're going to have the tension up that's holding that mass, and 98 newtons down. Now, which one's greater, or are they equal? If they're equal, then it won't be accelerating at all. So the weight downward has to be greater than the tension upward. So we're going to have a 98 minus t equals 10a for that translational application of Newton's second law. Now we go back to this rotational piece. How do we bring in the a and the alpha? How do we bring those together? We also have this unknown tension t. So we have two equations with two unknowns here. Actually, two equations with three unknowns. We actually need a third equation. But remember, there's a relationship between alpha and a. This a, the end of the beam, is going to be accelerating at the same rate as the mass going downward. So this is the edge acceleration of the beam out here, which means we can unpack A equals R alpha. Don't ever forget those. If you have two expressions, one with alpha, one with A, this is the connecting piece. A equals R alpha. So if we plug A equals R alpha in right over here, right over there, you have a lot of lines going in every which way. There we go. If we plug in A right over here equals R alpha, R being 5, then we have two equations with two unknowns. 98 minus t equals 50 alpha, and then we're going to have this expression up here that you can simplify. T alpha alpha. It's two equations and two unknowns. Just remember, this bar is rotating with that translating mass, so you have to account for both of those. And we get an alpha of 1.79 radians per second squared. Don't get caught and forget to take into account that moving mass, the translating mass, and the rotating beam. They're working together. They both have mass, so they both have an inertial mass. They both have inertia, and it's going to affect the acceleration of the system. Okay. Example 3. What if we have a rotating disk? Now the disk has an inner chunk to it. Let's say there's a smaller piece of the disk and a larger piece of the disk. And on the smaller piece of the disk is wound around it a 30 kilogram mass and on a string. And around the outside is a 10 kilogram mass on the string. All right, so what will be the, and there's the 1 meter is the inner radius and 2 meters is the outer radius. Okay, if the this strange disk system has a rotational inertia of 1.5 kilograms meters per second, kilograms meters squared, not meters per second, then the alpha is what we're looking for. So if we sum the torques here, we're going to have a 9.8 times 10, which is the weight of the outer mass, times 2. So that's the torque. That'll be the weight times the torque arm. Minus, going the other way, is this 30 kilogram mass times 9.8 would be weight, but its torque arm is only 1 meter there. So we're going to subtract those. The 10 kilogram mass is trying to rotate the system clockwise, and the 30 kilogram mass is trying to rotate the system counterclockwise. So we're going to get a 196 minus 294. Oh, I picked the wrong direction of the positive angular acceleration, but that's okay. We're going to get a negative, which just means it's the other way. So if I'm saying positive is clockwise, that means a negative is going to be counterclockwise. So when you work it out, you get 65 radians per second squared counterclockwise. And that's because we had a negative 65 clockwise. All right. And okay, moving on to, I promised a few sessions ago we'd be looking at conservation of energy with rotational kinetic energy. So here it is. If you had a block or a car going down, we just have potential energy plus kinetic energy at the beginning equals kinetic energy at the end. And what if it hits a spring? Now, what if we add in here, what if this is a rolling object like a disk, okay, or something like that? What would happen then? Well, that's solving for the cart. All right, if we had a solid wheel, I think that's what this is. Yep. All right, we would have the potential energy at the top plus the translational kinetic energy. Remember that center of mass of the wheel is translating, so we do have to include that. That would be the mass of the wheel plus the rotational aspect of it. It's hard to get it going. It's got to rotate all that mass about the center of mass. So that wheel will have a rotational inertia I, and its initial omega squared. And at the very bottom, there will be no more potential energy. So notice there's no more potential energy over here at the bottom. But there's only translational kinetic energy and rotational kinetic energy. So what we're going to do is substitute in. We have to relate the translational kinetic energy to the rotational, and the connection there is that the center of mass velocity of this wheel is equal to the edge velocity of the wheel. So if the edge velocity relates to the angular velocity of the wheel, then we can substitute all those in. So we're going to have an mgho plus 1/2 mv squared, that's translational kinetic energy, plus we're going to substitute I is for a solid disk is 1/2 mr squared, and the omega, using v equals r omega squared is v squared over r squared. Plug that in both sides. It looks a little sloppy here. If you plug in a bunch of numbers and solve, the only thing we got as an unknown is the final velocity. So we're going to factor that out. Or actually, it turns out we can combine like terms down here and solve for a final velocity of that wheel. Okay. Make sure I didn't miss anything here. Oh, another situation you might have, just generically, for rotation, you might have a pendulum. And so this works as well. It could be a regular pendulum or a physical pendulum. That'll be covered in our last session with oscillations. We're looking at energy. All right, and finally, conservation of angular momentum. I think I've got the one case here. Maybe I have a couple of examples. Oh, good, I have a couple of examples. All right. So beforehand, we have when we were looking at this before, conservation of momentum, we have a couple objects crashing together. They're only moving with translational momentum here. So we had the initial momentum of the two objects equals the final momentum of the two objects. For inelastic collision, we'd have the initial momentum equals the final momentum of that conglomerate piece that's stuck together. Now, what if we have like a merry-go-round, all right? And we have the riders moving in or out, all right? So there's not really a change or a collision here, but there is a change in the mass distribution of this object. So you've got the merry-go-round by itself, it's not going to change its mass distribution, so it'll just spin, spin, spin indefinitely unless there's some friction in it. Now if this is there's going to be an object jumping onto the merry-go-round. I kind of gave a hint to that before. What will be the final angular momentum? So here's a good problem. It involves the angular momentum of the disk and the angular momentum of this moving point mass. So the point mass has a rotational inertia of mr squared. Now it's going to jump on the end here, so r is going to be the radius of the disk. Now the initial momentum is going to be mv, but since it's going to jump onto the disk, we're going to use an mvr. So there's two ways to look at it. We could just use the mv or mr squared is the rotational inertia, and omega equals v over r. That gives us a relationship between the dude's translation to the rotation once he or she jumps on there. So you plug that in, you get mr squared times v over r. You end up with mvr. So I want to remind you that you could also use that second expression for angular momentum. That would be mr cross v. mr cross v would also give you the same expression. When you look at the angle at which the dude jumps on the merry-go-round, it is a perpendicular angle. So mr cross v would be better. What if the person jumped on kind of at an angle to the merry-go-round? Then you would have to include an angle, and you don't quite get that here with this method of solving. So do remember that. So we're still using an initial momentum equals a final momentum of the system. So initially we're going to have the angular momentum of the dude and the angular momentum of the merry-go-round if we add this together. And they're going to combine into one piece. So this would be angular momentum of both. This is like an inelastic collision. So the angular momentum of the dude is mvr. The initial angular momentum of the merry-go-round is 0. It's at rest. So afterwards, they're going to be combined. So what's the rotational inertia of both of them times the angular velocity of both of them? So we're using the I omega form of angular momentum here. So here we have the initial velocity times the momentum of the dude times r equals, and afterwards the dude's still on there, so dude has a rotational inertia of mr squared. If this merry-go-round is a disk, we're going to use 1/2 mr squared as the I. To combine those two, we're going to just add rotational inertias, just like we add mass if the two masses combine. Here we have two masses combining into one, but they're in a rotational system. So when you use the rotational inertia times the final omega, final angular velocity, plug in the mass of the dude, the velocity of the dude, times the radius of the merry-go-round where the dude's jumping on. Now if you jumped halfway in, then we'd only put a 1 here. But since he's jumping on the end of the merry-go-round, we'll put a 2 here. The radius of the merry-go-round is 2 meters. And afterwards, the dude is going to be located at 2 meters. So the rotational inertia doesn't change for the dude. But since the merry-go-round is going to be moving at the end, we're going to include the mass of the merry-go-round, 1/2 r squared. This is the rotational inertia of the merry-go-round. And we sum that up, multiply by the final angular velocity, and that's how you get it. Okay? Know how fast it's spinning. And one more system. This is a prelude to our last session. What if you have a planet orbiting a star? Then it's not the mass really changing, and this isn't like a disk or anything, but it's a mass located at a radius r. So the best thing to use here is mrv, mr cross v, or mvr. So if we're looking at this position and this position, the angle between r between the sun and the planet, and this r between the sun and the planet when it's out here, the angles are always perpendicular. They're always 90 degrees. So we just got mvr initial equals mvr final. So what we can get out of this is the the near velocity of the planet in its elliptical orbit and the far velocity of the planet in its elliptical orbit. In this case, we know the far velocity is 1,000 meters per second. And so what's the near velocity? This is I think I'm using a radius of 1 times 10 to the 30 there. It looks like the mass of the planet cancels. So the initial velocity, or the velocity out in the far regions, is 1,000 times 1,000 times 1 times 10 to the 30. So it would be the velocity on its closest approach, where it's r is 1 times 10 to the 28. It would be 100,000 meters per second. So it does get faster as it gets closer and slower as it gets further out. All right. So that's another application of that. Angular momentum, conservation of angular momentum. I hope this presentation has been helpful. Good luck on the test coming up.